in no more than 7 or 8 hours. We are no less helpless in the face of cold. Like all mammals, humans are good at generating heat, but because we are so nearly hairless, we are not good at keeping it. Even in quite mild weather, half the calories you burn go to keep your body warm. Of course, we can counter these frailties to a large extent by employing clothing and shelter, but even so, the portions of the earth on which we are prepared or able to live are modest indeed. Just 12% of the total land area, and only 4% of the whole surface if you include the seas. Yet when you consider conditions elsewhere in the known universe, the wonder is not that we use so little of our planet, but that we have managed to find a planet of which we can use even a bit. You have only to look at our own solar system, or come to that, the Earth at certain periods in its own history, to appreciate that most places are much harsher and much less amenable to life than our mild, blue, watery globe. So far, space scientists have discovered about 70 planets outside the solar system, out of the 10 billion trillion or so that are thought to be out there. So humans can hardly claim to speak with authority on the matter, but it appears that if you wish to have a planet suitable for life, you have to be just awfully lucky. And the more advanced the life, the luckier you have to be. Various observers have identified about 24 particularly fortunate breaks we have had on the Earth, but this is a flying survey, so we'll distill them down to the principal 4. Excellent location. We are, to an almost uncanny degree, the right distance from the right sort of star, one that is big enough to radiate lots of energy, but not so big as to burn itself out swiftly. It is a curiosity of physics that the larger a star is, the more rapidly it burns. Had our sun been 10 times as massive, it would have exhausted itself after 10 million years, instead of 10 billion, and we wouldn't be here now. We are also fortunate to orbit where we do. Too much nearer, and everything on Earth would have boiled away. Much further away, and everything would have frozen. In 1978, an astrophysicist named Michael Hart made some calculations and concluded that the Earth would have been uninhabitable had it been just 1% further from or 5% closer to the Sun. That's not much. The figures have since been refined and made a little more generous. 5% nearer and 15% further are thought to be more accurate assessments for our zone of habitability, but that is still a narrow belt. To appreciate just how narrow, you have only to look at Venus. Venus is only 25 million miles closer to the Sun than we are. The Sun's warmth reaches it just 2 minutes before it touches us. In size and composition, Venus is very like the Earth. But the small difference in orbital distance made all the difference to how it turned out. It appears that during the early years of the solar system, Venus was only slightly warmer than the Earth and probably had oceans. But those few degrees of extra warmth meant that Venus could not hold on to its surface water, with disastrous consequences for its climate. As its water evaporated, the hydrogen atoms escaped into space, and the oxygen atoms combined with carbon to form a dense atmosphere of the greenhouse gas carbon dioxide. Venus became stifling. Although people of my age will recall a time when astronomers hoped that Venus might harbor life beneath its padded clouds, possibly even a kind of tropical verdure, we now know that it is much too fierce an environment for any kind of life that we can reasonably conceive of. Its surface temperature is a roasting 470 degrees Celsius, which is hot enough to melt lead. And the atmospheric pressure at the surface is 90 times that of Earth, more than any human body could withstand. We lack the technology to make suits or even spaceships that would allow us to visit. Our knowledge of Venus's surface is based on distant radar imagery and some startled squawks from an unmanned Soviet probe that was dropped hopefully into the clouds in 1972 and functioned for barely an hour before permanently shutting down. So that's what happens when you move 2 light minutes closer to the Sun. Travel further out, and the problem becomes not heat, but cold, as Mars frigidly attests. It too was once a much more congenial place, but couldn't retain a usable atmosphere and turned into a frozen waste. But just being the right distance from the sun cannot be the whole story, for otherwise the moon would be forested and fair, which patently it is not. For that you need to have the right kind of planet. I don't imagine even many geophysicists, when asked to count their blessings, would include living on a planet with a molten interior, but it's a pretty near certainty that without all that magma swirling around beneath us, we wouldn't be here now. Apart from much else, our lively interior created the outpourings of gas that helped to build an atmosphere and provided us with a magnetic field that shields us from cosmic radiation. It also gave us plate tectonics, which continually renews and rumples the surface. If the Earth were perfectly smooth, it would be covered everywhere with water to a depth of 4 kilometers. There might be life in that lonesome ocean, but there certainly wouldn't be football. In addition to having a beneficial interior, we also have the right elements in the correct proportions. In the most literal way, we are made of the right stuff. This is so crucial to our well-being that we are going to discuss it more fully in a minute. But first, we need to consider the 2 remaining factors, beginning with another one that is often overlooked. We're a twin planet. Not many of us normally think of the moon as a companion planet, but that is in effect what it is. Most moons are tiny in relation to their master planet. The Martian satellites of Phobos and Deimos, for instance, are only about 10 kilometers in diameter. Our moon, however, is more than a quarter the diameter of the Earth, which makes ours the only planet in the solar system with a sizable moon in comparison to itself. Except Pluto, which doesn't really count because Pluto is itself so small. And what a difference that makes to us. Without the moon's steadying influence, the Earth would wobble like a dying top, with goodness knows what consequences for climate and weather. The moon's steady gravitational influence keeps the Earth spinning at the right speed and angle to provide the sort of stability necessary for the long and successful development of life. This won't go on forever. The moon is slipping from our grasp at a rate of about 4 centimeters a year. In another 2 billion years, it will have receded so far that it won't keep us steady, and we will have to come up with some other solution. But in the meantime, you should think of it as much more than just a pleasant feature in the night sky. For a long time, astronomers assumed that either the moon and the Earth formed together, or that the Earth captured the moon as it drifted by. We now believe, as you will recall from an earlier chapter, that about 4.4 billion years ago, a Mars-sized object slammed into Earth, blowing out enough material to create the moon from the debris. This was obviously a very good thing for us, but especially so as it happened such a long time ago. If it had happened in 1896, or last Wednesday, clearly we wouldn't be nearly so pleased about it. Which brings us to our 4th, and in many ways most crucial consideration: timing. The universe is an amazingly fickle and eventful place, and our existence within it is a wonder. If a long and unimaginably complex sequence of events stretching back 4.6 billion years or so hadn't played out in a particular manner at particular times, if, to take just one obvious instance, the dinosaurs hadn't been wiped out by a meteor when they were, you might well be a few centimeters long, with whiskers and a tail, and listening to this in a burrow. We don't really know because we have nothing else to which we can compare our own existence. But it seems evident that if you wish to end up as a moderately advanced thinking society, you need to be at the right end of a very long chain of outcomes involving reasonable periods of stability, interspersed with just the right amount of stress and challenge. Ice ages appear to be especially helpful in this regard, and marked by a total absence of real cataclysm. As we shall see in the pages that remain to us, we are very lucky to find ourselves in that position. And on that note, let us now turn briefly to the elements that made us. There are 92 naturally occurring elements on the Earth, plus a further 20 or so that have been created in labs. But some of these we can immediately put to one side, as in fact chemists themselves tend to do. Not a few of our earthly chemicals are surprisingly little known. Astatine, for instance, is practically unstudied. It has a name and a place on the periodic table next door to Marie Curie's polonium, but almost nothing else. The problem isn't scientific indifference, but rarity. There just isn't much astatine out there. The most elusive element of all, however, appears to be francium, which is so rare that it is thought that our entire planet may contain at any given moment fewer than 20 francium atoms. Altogether, only about 30 of the naturally occurring elements are widespread on Earth, and barely half a dozen are of central importance to life. As you might expect, oxygen is our most abundant element, accounting for just under 50% of the Earth's crust. But after that, the relative abundances are often surprising. Who would guess, for instance, that silicon is the second most common element on the Earth, or that titanium is 10th? Abundance has little to do with their familiarity or utility to us. Many of the more obscure elements are actually more common than the better-known ones. There is more cerium on Earth than copper, more neodymium and lanthanum than cobalt or nitrogen. Tin barely makes it into the top 50, eclipsed by such relative obscurities as praseodymium, samarium, gadolinium, and dysprosium. Abundance also has little to do with ease of detection. Aluminium is the fourth most common element on Earth, accounting for nearly 1/10 of everything that's underneath your feet. But its existence wasn't even suspected until it was discovered in the 19th century by Humphrey Davy. And for a long time after that, it was treated as rare and precious. Congress nearly put a shiny lining of aluminium foil atop the Washington Monument to show what a classy and prosperous nation we had become. And the French imperial family in the same period discarded the state silver dinner service and replaced it with an aluminium one. The fashion was cutting edge, even if the knives weren't. Nor does abundance necessarily relate to importance. Carbon is only the 15th most common element, accounting for a very modest 0.048% of the Earth's crust. But we would be lost without it. What sets the carbon atom apart is that it is shamelessly promiscuous. It is the party animal of the atomic world, latching on to many other atoms, including itself, and holding tight, forming molecular conga lines of hearty robustness, the very trick of nature necessary to build proteins and DNA. As Paul Davies has written, if it wasn't for carbon, life as we know it would be impossible. Probably any sort of life would be impossible. Yet carbon is not all that plentiful, even in us who so vitally depend on it. Of every 200 atoms in your body, 126 are hydrogen, 51 are oxygen, and just 19 are carbon. Other elements are critical not for creating life, but for sustaining it. We need iron to manufacture hemoglobin, and without it, we would die. Cobalt is necessary for the creation of vitamin B12. Potassium and a very little sodium are literally good for your nerves. Molybdenum, manganese, and vanadium help to keep your enzymes purring. Zinc, bless it, oxidizes alcohol. We have evolved to utilize or tolerate these things. We could hardly be here otherwise. But even then, we live within narrow ranges of acceptance. Selenium is vital to all of us. But take in just a little too much, and it will be the last thing you ever do. The degree to which organisms require or tolerate certain elements is a relic of their evolution. Sheep and cattle now graze side by side, but actually have very different mineral requirements. Modern cattle need quite a lot of copper because they evolved in parts of Europe and Africa where copper was abundant. Sheep, on the other hand, evolved in copper-poor areas of Asia Minor. As a rule, and not surprisingly, our tolerance for elements is directly proportionate to their abundance in the Earth's crust. We have evolved to expect, and in some cases actually need, the tiny amounts of rare elements that accumulate in the flesh or fiber that we eat. But step up the doses, in some cases by only a tiny amount, and we can soon cross a threshold. Much of this is only imperfectly understood. No one knows, for example, whether a tiny amount of arsenic is necessary for our well-being or not. Some authorities say it is, some not. All that is certain is that too much of it will kill you. The properties of the elements can become more curious still when they are combined. Oxygen and hydrogen, for instance, are two of the most combustion-friendly elements around, but put them together and they make incombustible water. Odder still in combination are sodium, one of the most unstable of all elements, and chlorine, one of the most toxic. Drop a small lump of pure sodium into ordinary water and it will explode with enough force to kill. Chlorine is even more notoriously hazardous. Though useful in small concentrations for killing microorganisms, it's chlorine you smell in bleach. In larger volumes, it is lethal. Chlorine was the element of choice for many of the poison gases of the First World War. And as many a sore-eyed swimmer will attest, even in exceedingly dilute form, the human body doesn't appreciate it. Yet put these two nasty elements together, and what do you get? Sodium chloride, common table salt. By and large, if an element doesn't naturally find its way into our systems, if it isn't soluble in water, say, we tend to be intolerant of it. Lead poisons us because we were never exposed to it until we began to fashion it into food vessels and pipes for plumbing. Note, incidentally, lead's symbol is Pb for the Latin plumbum, the source word for our modern plumbing. The Romans also flavored their wine with lead, which may be part of the reason they are not the force they used to be. As we have seen elsewhere, our own performance with lead, not to mention mercury, cadmium, and all the other industrial pollutants with which we routinely dose ourselves, does not leave us a great deal of room for smirking. When elements don't occur naturally on Earth, we have evolved no tolerance for them, and so they tend to be extremely toxic to us, as with plutonium. Our tolerance for plutonium is zero. There is no level at which it is not going to make you want to lie down. I have brought you a long way to make a small point. A big part of the reason that Earth seems so miraculously accommodating is that we evolved to suit its conditions. What we marvel at is not that it is suitable to life, but that it is suitable to our life. And hardly surprising, really. It may be that many of the things that make it so splendid to us, well-proportioned sun, doting moon, sociable carbon, more molten magma than you can shake a stick at, and all the rest, seem splendid simply because they are what we were born to count on.